the trapezoidal rule. Another method of approximation. We have seen LRAM, MRAM, and RRAM can be used to approximate integrals. So, boy, it seems like a long time ago, but it wasn't that long ago. It was just earlier this week when we were drawing these rectangles, and the left-hand side of the rectangle would touch the curve, or the middle of the rectangle would touch the curve, or the right side of the rectangle, and we're using this to approximate areas. And now we are quite happy to include pictures with negatives in them because we're not scared of negatives anymore. We just know what that means now. Not a big deal. So shapes other than rectangles can be used to approximate integrals, often with more efficiency. They give better approximations than rectangles, and especially for a small number of intervals. That's the big thing, is when you use a large number, rectangles works fine. But who wants to use a large number? Like, oh, well, we got the integral now. What do we care? I'm like, oh, I know. There's more to the story than just grinding the integrals out. An example of a trapezoidal approximation. Here's a curve, this red curve, that is very curvy. And these are the kind of curves that throw the rectangular approximation off, because the rectangles don't match up very well. But you can see how the trapezoids match up very nicely, because they follow along with the slope of the curve to some degree. They're not perfect, yeah, but they follow along to some degree. And I want to come back to this picture later. This is a great picture of something else I'm going to talk about during the lesson. So consider the following graph of y equals f at x, in which the interval a to b is partitioned into n subintervals. So we've got some, and again, now look at the pictures. We're drawing pictures with negatives because we're like, yeah, no big deal. So, and then you divide it up into these partitions. And again, these partitions don't have to be equal size, but it's much easier if you do use equal size. And so you divide it up like we've done before. We call the first one A, we call the last one B, but that's just really x0, the lowest x, and xn, which is the highest x for whatever interval you're going to be talking about. And so the length of each interval is h equals b minus a over n. This is the first difference in this lesson. You're like, isn't that just delta x? We've been calling that delta x. We've been calling that the width of each of these intervals. And the answer is, yeah, it's the same thing. Just we're going to call it h, and you're going to see why in a second why it's nice to call it h. It's just convenient to call it h. So each of those little intervals has a little height, if you want. Yeah, I'm turning my head sideways. Each little interval has a height. The region between the curve and the x-axis is approximated using trapezoids. Here they come. Trapezoid, 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 trapezoid. Lots of little trapezoids, and hopefully you see the advantage of trapezoids. They can, in a small number of rectangles, they might do a better job. I say might do a better job. Usually they'll do a better job than rectangles will. So I just want to talk about these points. To get the individual y values at each endpoint of the trapezoid, you just sub in the x values like we were doing before. You sub in x0 to get that y value, and then you sub in x1 to get that y value, x2 to get that y value. That's all the same as what we were doing before, all the way up to the end. The only difference is, in each interval, we'll need to know both y values. Don't let that scare you. This doesn't turn into, it's a long calculation, but it's not as long as you might be scared that you're like, oh, here we go with all this stuff again. And it's not nearly as bad as you think it's going to be. Question for discussion. What happens in the fifth trapezoid? Let's see. Trapezoid 1, no problem. Trapezoid 2, no problem. Trapezoid 3, no problem. Trapezoid 4. Trapezoid 5 has a positive and a negative component to it within the same trapezoid. And actually, if you think back, that could maybe happen with the rectangles too. You're like, well, which one do we use? Do you use this endpoint? Do you use that endpoint? And as it turns out, it doesn't really matter. See, these little areas are so small that using the positive version or the negative version doesn't throw you off any more than the little piece. See how big a piece it missed up here? You know? So yeah, you're going to miss a piece here, depending on which one you choose, but that's all part of the approximation. So the fact that it goes positive and negative, again, doesn't really affect the overall answer all that much. You're like, yeah, look, it's going to throw it way off. Yeah, it's an approximate. It's going to be thrown off. There's going to be times when it's thrown off, and then it definitely gets thrown off in that little section right there. Okay, so here's the same picture from the previous slide. Recall the area of a trapezoid. Maybe you don't remember the area of a trapezoid. The area of a trapezoid is height times average width. That's how I remember it. Not length times height like a rectangle. It's length times take the top and bottom of the trapezoid and divide by 2. And that will give you the area of a trapezoid. But the trapezoids are sideways here. Can you see the trapezoids are like on their side here? So the height is this way. It's the delta x. That's why we called it h. Those h's are the heights of the little trapezoids. So we've got the first y value and the second y value and the height. It's sort of that simple. That's all the only three things we need. Therefore, what therefore? And then a whole big thing comes up. Let's just talk about the first one, okay? Let's talk about this first trapezoid right over here. The farthest left trapezoid. If we wanted to find its area, we'd go h, which is its height. H, yes? Then we'd average the top and bottom widths, which are y0 and y1. So you go y0 plus y1 divided by 2. Then you go to the next trapezoid. Height times average the y1 and the y2. Then the next one, the next one. It's the same all the way along. Your very last one will be h, the second last y value and the last y value averaged to get the area of the last trapezoid. When you see that expression, you might be thinking, oh, here, this is exactly what you said was not going to happen, is that we're going to have this big nightmare. No, this is just the first line of all this. Yeah? That's in theory what you have to do, but we can do some algebra to make this trapezoid rule a lot better. A lot better. That is, the common factor is h. H is in all of them. And even better, the over 2 is in all of them. So when you pull h out, oh, sorry, I don't want to pull the over 2 over. I pull the h out, but I don't pull the over 2. Because watch, I'm going to do some highlighting here. I just want to highlight one of these, and it's enough that you can see the rest of them. So cool what happens here. Okay, highlighter. Oh, so okay, look right there. Right in that term is y1 over 2. Awkward, because it's a fraction. And the very next term says, oh, I've got a y1 over 2 over here as well. See, y1 over 2 and y1 over 2. And half of y1 and half of y1 is a full y1. And then it happens every single pair all the way along the way. Every time you have a y value over 2, there's a matching one over in the next bracket that you can add with it. And what you end up with is all these ones in between. Don't worry about the outside ones for a second. All the ones in between, you get y1 plus y2 plus, you're just adding up all the different y values. Except for the first one, it doesn't have a pair. And the last one, it doesn't have a pair. Weirdly, they're sort of each other's pair in the algebra of all this. And so you get this nice formula, which, let's just describe this in words. Take your height, then add up all the y values, except the first and the last one, which the first and the last one you got to divide by 2. This is tidied up one step more. I've pulled the half out front, which I went to do at the start, but maybe it's a little easier to do it at the end. When I common factor the half out front, the first and the last then become 1, and all the ones in between become 2s. That's the way to really remember it. That's a handy way to use it. 1 twice all the rest of them, and 1 times the last one. I'm going to explain this another way in just a second because it might seem weird that those have all appeared. Basically, what you end up with is a list that's y0, y1, y2, y3, all the way to the end, and then you start again at y1 and add all those, so you get the endpoints once, but everything else in between you get twice. It's LRAM and RRAM. It's LRAM added with RRAM, and when you put all those together, you get the left endpoint once in LRAM, and you get all the other points in between. When you do RRAM, you get all the other y values, but then you get the right endpoint as well, once. And so that's how you end up with LRAM plus RRAM. And then it's divided by 2, so it's an average. It's just an average of LRAM and RRAM. Which is, after you see that, you're like, maybe you could have just explained it that way, actually. And that's what happens in the next slide. It's just LRAM and RRAM divided by 2. Yeah, it's just the average of those two, which sort of makes sense that you'd go halfway in between these two to get a better approximation. LRAM will be either too big or too small. RRAM will be either too big or too small, but average those and you're going to get something close to the middle. Why is the above expression, I explained that. So, to approximate, okay, big moment of the lesson though, the one little thing that can mess you up, one of the examples is, to approximate the integral, we could do this. Total area is h over 2, add up all the y values, but 2 for all the middle ones, just 1 on the endpoints. You don't have to memorize this. I'll write it on the board the day of your test. I want you to be able to use it. not get hung up in memorizing this, because there's another one coming. I don't want you to confuse the two. Okay? So I'm just going to write it on the chalkboard over here on the side here. So when we want it, it'll be available to us. Total area equals h over 2, y0 plus y1 plus y2, just keep, 2y1 plus 2y2 plus 2y3. Keep adding 2 of them until the last one where you only add 1 of them. Okay? That's the trapezoidal rule. Maybe T stands for trapezoid instead of total area. I'm not actually sure which one it means. Did I finish talking about that? Yes. This trapezoidal rule is just LRAM plus RRAM divided by 2. It's the average of the LRAM and the RRAM. Oh, examples. Right to examples. I've got an example page on a separate deal here. Is this the right first example? Use the trapezoidal rule with n equals 4 to approximate integral 1 to 2 of x squared dx. Now, incidentally, if you're out there thinking, you should be thinking, we now have a better way to do this. Isn't the fundamental theorem way more efficient on this? Bang, bang, done? Yeah? And the answer is, well, yes, but you saw the problems the calculator had with some of the integrals and some of the Riemann sums we did. This is warming up for tougher situations is what we're trying to do here. We're trying to come up with something that can be used as a computer program to calculate integrals very quickly and easily as opposed to going through a lot of different steps. Okay. Integral 1 to 2 of x squared. Okay, in these questions, the very first thing to do is get this h. The formula screams it. T equals h over 2. The very first thing you want is h. And h, I'm going to write over here because I want to have room for a graph. H is equal to b minus a over n. I mean, that's the delta x. And we're only calling it h so that we remember it's the height of the individual trapezoid in the picture. So b minus a, what do we got? We're trying to do interval 2 minus 1. And how many n's? How many trapezoids? 4 trapezoids. So each of these trapezoids will be 1/4 wide. And some of the nasty pictures in the PowerPoint might serve to confuse you. There's supposed to be a big picture of what's going on, but it might help to actually see me actually draw this whole thing out so you can see exactly what we're talking about in those crazy pictures. So I'm just going to draw an x-axis along here. Maybe I'll do all the work over here. I'll make it nice and big. Okay, and so we're trying to find from x equals 1. I said 1 and wrote 2 there. Over to x equals 2. And we want to find the integral from 1 to 2 of x squared. Now, I always sort of draw the same picture when I'm doing stuff like this. I just draw a nice increasing function because I find that easier to draw with. And I know in my head whether this thing goes up or down, positive or negative, the numbers will bear that out. This just is nice and easy for me. So each interval is 1/4 wide. So 1, 5/4, 3/2, and 7/4. I hope my fraction work isn't messing you up. In earlier examples, I went through and I went, oh, well, this is 4/4, 5/4, 6/4, 7/4, 8/4. And if you're still like that with your fractions, yeah, that's fine. You go ahead. I just am trying to advance here a little bit with my fractions. And so, my little trapezoids, let's talk about the first trapezoid. Can you sort of see the first trapezoid there? Yeah, I know it's curved, so it's not going to be perfect, but that's sort of the first trapezoid. So what I need is this y value, 1 comma, and I need that first y value. And then I need this y value. It'll be 5/4 comma y value. Then I need this y value. 5/4, no, 3/2. Not 3/2, 5/4, silly. 3/2, comma, the y value. And then here, 7/4, comma, the y value. And then here, 2, comma, the y value. It makes your life a little easier if you simplify those fractions in there. You're not subbing in 8/4 when you could be subbing in 2. And I've given away the answer to my next question. How do I get the y values here? To go with these? Yeah, just sub it back in. So I get 1 squared. I get 5/4 squared. I get 3/2 squared. I get 7/4 squared. And I get 2 squared. And now I'm going to switch colors so you don't get confused because I've made this diagram bigger than I should have for what I have to write next, which is what you'll copy down off the board and on the homework. Yeah? We're not in the business of memorizing the trapezoidal rule here. We want to be able to use it. You got to be able to look at it and know what it does. So here's the trapezoidal rule. The trapezoidal rule says T equals h over 2. Y0 plus 2 of the y1s plus 2 of the y2s plus ... plus 2 of the second last one plus only 1 of the last one. In this case, though, it's y0 plus 2 y1s plus 2 y2s plus 2 y3s plus y4. Those are the only ones in my trapezoidal rule. I only have 5 points. So I've got 3 of these middle points and then the 2 outside points for my trapezoids. Now I can actually fill in the numbers. H was 1/4. I'm going to divide that by 2. Y0 was 1 squared, then 5/4 squared. Well, 2 5/4 squared. I forgot the 2 there. Oh, I thought my computer was going to hitch there, but it decided not to. 2 times 5/4 squared plus 2 times 3/2 squared plus 2 times 7/4 squared plus 2 times, oh, not 2, the last one's not 2. The last one's just 2 squared. And those are just the y values that I've subbed in. 2 of all the y values except the endpoints. The endpoints we only get once. Well, I'm going to try and do a lot of this in my head just to try and stay young here. 1 plus, let's see, 25/16 times 2 is 25/8. And 9/4 times 2 is 9/2. And then 49/16 times 2 is 49/8 plus 4. Let's move this up and out of the way. Excuse me. Can you sit there, please? Thank you. And then t equals 1/8. Ooh, I guess I need all 8s here, do I? 8/8, 33/8, 36/8 is 79/8, 110, 127, 132, 139/8. Oh, I don't trust those numbers in my head. Here, I'm going to put them over here, 139/64. I feel like there's a mistake. I'm going to do it again in my head. 5/4 squared is 25/16. Yes. 9/4 times 2 is 9/2. 49/16 times 2 is 49/8 and 4. And then all the 8s. I got lots of 8s here. 8, 33/8, and 36 is 74/8. 123/8, and 32/8 is 155/8. Oh, don't lock up now. Come on, I'm almost home. Oh, I'll write them out. Jeez. Computer hitched there on me. Lost my concentration. Or maybe I'm just old. It's because I'm 48 now. I'm 384/8. That's why. Equals. Now I can do them. (145/64). Is it right? No, it's not. It says 150. My notes say 150. 33, 69, 113, 145. Where did I lose something? Calculator. He broke down and got his calculator out. 1 squared plus 2 times 5 quarters squared plus 2 times 3 halves squared plus 2 times 7 quarters squared. Oops. Did that wrong. Close bracket. Squared. Plus 2 squared. 75 over 4. So that must have been 150 somehow. So where's my mistake? It's driving me nuts. 25 over 16, 50 over 16, which would be 25 over 8. 9 over 4 times 2 is 18 over 9 over 2. 49 over 16 times 2 is 49 over 8. And then the number 4. 8 over 8, 25 over 8, 36 over 8, 49 over 8, 32 over 8. Add it the other way. 81, 117, 142, 150. It was just the adding. 33, 69, 113. 150. It is 150. Oh, all right. $75 over 32. Oh, 118 plus 32 was 150. All right. Any questions about that? You don't do all that. You just punch in your calculator. I'm just trying to stay young. I'm just trying to stay on top of these things. 75 over 32. That's the area under that curve because the integral's all positive there. But anyways, B, compare your approximation to the exact value. Oh, a little practice on regular integrals here. So B, exact value. Integral from 1 to 2 of x squared dx. 1/3 x cubed. Yes. Evaluated between 2 and 1 equals 1/3 of 8 minus 1/3 equals 23 and 2/3. No, 8/3 minus 1. No. 8/3 minus 1/3. 7/3. That's the actual answer. This is our approximation of the answer. Using only 4 trapezoids, by the way. Yeah? So let's see how good our approximation using trapezoid is, using only 4 trapezoids. So I don't know, where's your percent error? Where's your science people? Percent error is always measured minus actual over actual? Science people? No? Oh yeah, when you want to find out how far you're off, first find out how much you were off. But then we really want to know as a percentage. Yeah? Why as a percentage? Because, listen, if I do an estimate of where the office is from here, and I get it right to the nearest kilometer, that's not very good. That's a percentage of what the actual measurement was. That's not very good. But if I get the measurement from here to Mars off by 1 kilometer, that's pretty good. So you always want to divide by the actual to find, well, what percentage? How much was it off completely? So, okay, so measured minus actual, 75 over 32. Subtract the 7/3. And we're going to take that all and divide it by the actual, which is 7/3, to see what I get. I'm going to do that all on my calculator this time. Especially for you science people, because you probably would do this as a decimal. 75 over 32. Subtract 7/3 all over 7/3. 0.004, which would be 0.4%. Our area is only off by 0.4% with only 4 trapezoids. That's how good the trapezoidal method is. What questions do you have? More time here? Yeah, more time? I was going to say, I goofed around with those fractions for so long that you... Still staring at that addition that I got wrong there. You guys not do percentage error in chemistry? More physics. Yeah? Good? An observer measures the outside temperature every hour from noon until midnight, as shown in the table below. Estimate the average temperature for the 12-hour period. So to do this, what I'm going to do is h over 2 times y naught plus 2y1s plus 2y2s plus all the way along, and then I want the 11th one, and then the 12th one. I'm going to call those n's for now, because actually they're actually the 12th and 13th ones, but I don't want to confuse the issue with the crazy numbering system here. So this is n minus 1, just which means the second last one, and then add the last one. So I'm just going to use what we've been doing here. We'll talk about the h in just a second. The h is actually very simple here, but we'll talk about it in just a second. I'm just adding up, oh, can you believe this? 63 and 2 times 65 and 2 times 66 and 2 times 68 and 2 times, I gotta start pointing at them or I'm gonna forget where I am, 2 times 70, and then 2 times this 69, and then 2 times this 68, and then 2 times this 68. Good thing I was pointing at them, or I might have missed one of those 68s there, which would have thrown my answer off crazy. And then 2 times this 65, and then 2 times this 64, and 2 times this 62, and 2 times this 58, and then only add the last one once. Now, the h is just how wide these intervals are, which in this case is pretty straightforward. They're all 1 hour wide. You know, all the intervals are 1 hour wide, so I get this. So I get 1/2, and then I got to add all this crazy stuff up. Well, I'm not going to try and do that in my head on a Friday, I'll tell you that. Although it would be good for me. 2 times 65. I hope someone else is typing this in to check if I type this in right. Plus 2 times 68, plus 2 times 70, plus 2 times 69, plus 2 times that 68, plus 2 times that 68. Hey, missing a bracket there. Plus 2 times 65, plus 2 times 64, plus 2 times 62, plus 2 times 58, plus just 155. 1564. Anybody else? 15? Oh, Veronica's nodding. And then I need 1/2 of that. I get average temperature of 782. I hope you're with me, and I hope you're confused. All right? Because let's talk about what we've got here. Notice I left just an equal sign there. I didn't put anything out front. Yeah? Because I really want to talk about what we've calculated here and why this is clearly not the average temperature. Well, let's play silly for a second. I added them all up like it asked. y0 plus y1, no mistakes. h over 2, Veronica, check for me. When we add all this up, we're 72. Of course it's got to be big. I was adding up lots of big numbers. How is this actually going to find the average? Just rewind for a minute. What does this actually calculate? It's called t. I get it. It's called t. But way back when, what is it we were calculating? It's got a fancy word named t. But if we go back to the PowerPoint here, and we go here, and we go, what was this thing calculating? It's an approximate of the sum from a to b of f at x dx. It's an approximate of the integral. It's just adding these things up. It's not average value at all. Oh, this is total. Or maybe it's sum of the temperatures over time. Over time, not dx here. Over time this time. So how do I get from the integral to the average? I can't tell. Simon's hands. He wants to answer. Good. Do it. Do it. You tell me what do you think? Yeah. He's not reaching back to my yesterday's lesson. He's just reaching back to logic and going, well, there's 12 of these intervals. Wouldn't you just divide it by 12? Like, you've added up all the intervals, divide by 12 and it's over. And that's right. But did everyone sleep through the video yesterday? Did we do average value? Was there a video about average value yesterday? Oh, no, it was 2 days ago, was it? Which one was yesterday? I taught one, and I didn't teach the other one. I left one as a video. Let me write down. Average value of a function equals, is it ringing a bell yet? 1 over b minus a times the integral from a to b of f at x dx. So yes, you take the integral, and that'll give you the total area. You want to find the average and all that, you got to divide by how wide the integral was. So the average temperature here is 1 over 12 minus 0. The 12 Simon identified as the important feature of all this. We want 1/12 of that integral of 782. Let's see if that comes up with an answer that we can live with a little more. 782 divided by 12 intervals, 65.16. Okay, but let's do a 65 and a sixth. Even though in temperature, nobody would ever say that. Oh, 65 and 1/6 degrees out. You know what I mean? Obviously, in these type of situations, people are decimals. Does that make you feel better? Does that look more like what the average temperature might be in all that? Like, wouldn't I have done better just by adding up the temperatures and dividing by how many there was? Wouldn't that have done pretty much the same job? The answer is totally yes. We take this method and practice on nice, easy ones to get ready for more complicated situations. So I'm not for a minute suggesting anyone anywhere is using the trapezoidal rule to find average temperature over the day. No, I don't think that's happening anywhere, anytime. Absolutely not. We'd like to, like all high school math, we like to practice on easy ones so we're ready when the big ones come along. Any questions there? Consider the two graphs shown below. For each graph, state whether the trapezoidal rule will underestimate or overestimate. There was a great picture earlier that really shows this in the PowerPoint. Back to the PowerPoint. Right there. Take a look at the sections where the trapezoidal rule overestimates and the sections where the trapezoidal rule underestimates. There's a very specific thing going on for when it overestimates and when it underestimates. Let me draw it again. Here we were overestimating, all in there. And here we were always underestimating. Let's go back to our picture. Maybe I'll draw a little trapezoid on here to try and hook up 2 points in this section and in this section here. I'll draw a little trapezoid to try and help. So if I was to make a trapezoid from, say, here to there, and I hope the points are far enough apart that it becomes clear when I draw this, and I hook up a trapezoid in that section, do you see that my trapezoid would underestimate what's really happening here? And then if I draw a trapezoid over here, and I hope the points are far enough away that it's clear from your desk exactly what's happening there. That trapezoid overestimates. Under. Over. But in general, can you now see what types of curves will it underestimate and overestimate? So under qualification, over qualification. What was it about this curve here that made it underestimate the area? It's just concavity, yeah. Something about the double derivative here matters. But for us, it'll be enough to say concave down and concave up. Which begs the question, can we improve on the method of trapezoids if we get the concavity involved and try and improve on our estimate? And the answer is yes, not in this course, but if you're really trying to use this to do estimates, then you could use the second derivative to try and fix your estimate a little bit, because you'd know you were over and under a little bit. So there's more to the story here. Any questions there? More time? Okay, we're in the home stretch of this lesson, but not necessarily the day, but of this lesson anyway. So we did that, yeah, that was all that. Okay, yeah, we did all that. Okay, good. Oh, we highlighted some stuff. Okay, that was fun. And then we used it, and we did those 2 examples. Oh, we did the 3 examples. We did that. Okay, Simpson's rule. Okay, these got to be labeled. And again, Simpson's rule, when it comes up on the screen, if it seems pretty scary, don't worry too much about it, because we're not going to memorize it. Now, what's interesting about Simpson is he didn't discover this rule. He read it somewhere else and passed it along, but his book was more famous, so he gets credit for it, even though he never tried to take credit for it. He just said, hey, check this out, and then people attributed it to him. Simpson noticed the problem with the trapezoids and the concave up, concave down. He said, can we do a little better by, instead of using the top of the trapezoid as a straight line, can we use a little parabolic curve? And that allows us to match the curve right up. And then he did all the math involved. That development's tough. Tough. We could go through it, but it's heavy. And so we don't put that in this AP Calculus course. So he noticed the shortcomings, and he used curve pieces. Specifically, he used parabolas, and you can do even better. You can do better types of curves, but he just said, I'll just use parabolas to estimate the curve in each particular section. And after he did all his work, it still came down to something reasonably simple for Simpson's approximation, is if he wants to approximate the integral from a to b of f at x, he used this. The only qualification is it has to be an even number of intervals. There are adjustments that can be made, but Simpson's rule specifically is choose an even number. And because we're always free to choose how many intervals we're going to use, that's not really a big problem. So even number of intervals. And so if it's an even number of intervals, the first y value you just use as it is, then you use 4 of the next y value, then 2 of the next one, then 4 of the next one, then 2 of the next one, 4, 4, 2, all the way down, and then your last one you go back to 1 again. And if you use even, this will just work out nicely. It's been thought out, don't worry. If you use even, it works out very, very nicely. It says use your textbook or other resources to investigate the derivation. The derivation is not that crazy, but a little too much for us. And again, the h is just b minus a over n. It's the same delta x that we used before. There he is, Thomas Simpson. Notes, due to the use of parabolic arcs in the approximation, Simpson's rule is even more efficient than trapezoidal rule and therefore faster for computing approximations of integrals. I don't know what your calculator is using, whether it's just using Riemann sums, whether it's using trapezoids, or whether it's using Simpsons. Well, let's imagine for a second that right now that calculator has been programmed to use Riemann sums. It doesn't do integrals. It'll do Riemann sums. And you know those times where we've pressed equals and it like waits and waits and waits and waits? If somebody were to take that calculator and program Simpson's rule in, it wouldn't take that much time anymore, yeah? And maybe it's using Simpson's rule, and there's other versions. So that's how you would improve the software. And that's why code writing is so important, is to go, hey, I can improve this software. There's a better way to do it. And math is right tied to that, right? If you don't know the math, how can you possibly reprogram the computer to do a better job? The trapezoidal rule was discovered long before Thomas Simpson. He never laid claim to it, but rather only mentioned it in one of his textbooks. He brought it up in a textbook and said, hey, isn't this cool? And then later on, everybody's like, oh, it's Simpson's rule. Complete the last example of this lesson. I think I've got this on a separate deal here. Where is it? Right here. Use Simpson's rule with n equals 4. You know, and when I almost said if there, when I ask you to use Simpson's rule on the test, I won't use some crazy amount of rectangles of little arcs here. It'll be something under control. Oh, and I went over here and then got distracted, didn't I? I got talking about Simpson and I forgot to write this down. And I write it down dramatically here so that you can feel safe to know these things will be there for you when you go to use them. So it was y0 plus 4 of the next one, plus 2 of the next one, plus 4 of the next one, plus 2 of the next one. And it just keeps going like that until you get to your last one. Yeah, alternate between 4s and 2s for some reason. You know, he did some work and decided this was the best thing to do. Use Simpson's rule with n equals 4 to approximate this curve. Okay, so I draw the same picture every time when I do these. I go across like this. I get my x-axis going. And I get the lowest x value over here, 0. Highest x value over here, 2. And I draw a little curve like that. Doesn't matter what you draw. It's just for visualization purposes. And then you go, okay, n equals 4. Well, I got to do a little calculation up here. If I want my h, it's b minus a over n, like always. So it's 2 minus 0 over how many intervals? 4. And so I get 1/2 this time. We want intervals of 1/2. Notice, even. Simpson's rule with n equals 4. Had to choose even. So then I'm going, if they're half wide, I'm getting 4 rectangles. I sort of know what's going to happen here. We go 0, then we do 1/2, then we do 1/4, 1/2, 1/4. I was drawing backwards. 1/4, 1/2, 3/4. No, not 1/4. Last one was 1/4, right? 1/2, 1, 3/2, 2. There it is. I don't know why I was doing 1/4. Was the last one 1/4? Was the last? Oh, that's why. Okay. I'm not totally crazy. I'm a little bit crazy, but I'm not totally crazy with a randomly 1/4 is coming in. So then you need the y values for each of these sections. If you're going to use Simpson's rule, you need the y values that come out of these approximations. And actually, this picture of Simpson's rule is pretty close to what the little sections would look like, because his incorporates little arcs somehow. He used derivatives and double derivatives to come up with little arcs that he's going to use. So I need all these y values, 0, comma, well, 0. If I sub 0 into that 5x to the 4th, I'm getting 0, okay? The other ones I'll have to put them in there. So this next one's going to be 1/2, comma, 5 times 1/2 to the 4th. Now, I'm drawing the whole picture because I'm trying to still aim towards people who are having trouble with the whole big ideas here. When you're doing this yourself, I don't know if you need the whole picture to come up with these y values. All you need is the x values and sub them all in. You know, so you don't need this whole picture every time. Next one, 5 times 1 times 1 squared. Then 3/2, 5 times 3/2. 4th, power 4, yes? And then finally the last point was 2, comma, 5 times 2 to the 4th. So every one of those is power 4. Last question was power 2. 1/2 to the power 4, 1 to the 4. Okay, good. So now I'm ready to write down Simpson's rule. Simpson says take h over 3 and then go y naught plus 4 of the first y value, 2 of the second y value, then 4 of the third y value, 2 of the fourth y value, and then do nothing with the fifth y value. Just put it in there. So my h here was 1/2. So I get a 1/6 out front. I hope that wasn't too much of a shortcut for you. And then it's 0 plus 4 of the 5 times the 1/2 to the 4th, plus 2 of the 5 times 1 to the 4th, plus 4 1, 2, 3, 4, 5, 6. I don't have 6. I got 1, 2, 3, 4, 5. One, 4, 2, 4. Last one's 4. Oh, that's right. Over here. The last one before here is 4. Not 2, like I wrote down there. Okay, back to here. One too many in my original. All that. should have caught that at the beginning because it was 4, so this is n equals 4. Okay, so 4 of those, 2 of those, 4 of the y3s, which is 5 times 3 halves to the 4th, and then just the y4th, which is 5 times 2 to the 4th. Ooh, how am I feeling about doing these in my head today? 20 over 16 is the first one. That next one's just 10. Next one is 3, 6, 9, 3, 9, 27, 81 over 16. 81 over 4. 405 over 4? Oh, I'm going to my calculator in just a second. I'll try these out and then I'll check them. And then that's an 80. Let me type those in to make sure. See how I did. Four times 5 times 1 half. Exponent 4. How'd I do? 20 over 16? This one I don't need, yeah. Okay. 4 times 5 times 3 over 2. Exponent 4. 405 over 4 plus 80. Oh, that's good. Anyways, I'll go the rest of the way. 1/6 bracket 0 plus 20 over 16 plus 10 plus 405 over 4 plus 80 close bracket 385 over 12. 385 over 12 is what Simpson's approximation says. And this one again asks for percentage error, so I'll just scroll down. I don't think I've gone off the page there. I think everything's still there for you if you're still madly copying. So percentage error. Sorry, I thought you really knew this formula, so I'll write it a little more carefully. Measured, subtract actual over actual. So I think it's 385 over 12. But I need that actual number now. What's the actual area under here? So integral from 0 to 2 of 5x to the 4th dx. Antiderivative of 5x to the 4th. Easy little quiz right before lunch. How do we do antiderivative of 5x 4th? Look at the exponent and go one bigger. Start there, x to the 5th. And then go, okay, I'm going to multiply by 5, so I got to divide by 5 what's ever out there. Oh, it's a 1. So I'm actually doing x to the 5th is the antiderivative of 5x to the 4th. And some are so easy they just pop in your head. But I need to tell you, antiderivatives are not easy. I've been planting you with easy ones. But they are not easy. Sometimes they're impossible, actually, that no mathematician has figured them out yet, how to do an integral of certain functions. And so I get 32 minus 0 when I evaluate this is 32. So this is 385 over 12 minus 32 over 32. .26% error. We can really live with that, I think. Especially 4. A computer would have no problem with this. When it's all done, though, the blaring question should be, if this is so easy, like who in their right mind would do Simpson's rule and all that calculation, all the potential for error, and all the mucking around you saw me do to come up with this area when I can just go integral, evaluate, done. I've been trying to tell you something about integrals that tells you why we need things like Simpson's rule. Why do we need Simpson's rule if they're so darn easy over here? It's actually doing net area. This will handle it. When you do these, sometimes you'll get negatives. You'll get negatives in there. So this actually does the net area. This is a super easy integral antiderivative to do. And when they're super easy, things like Simpson's rule, nobody, I mean nobody, would do Simpson's rule on one that's so easy to take the antiderivative. But there's stuff coming. I'll write some easy ones. I think this is right. Integral of sine of x squared. We don't know how to come up with a good antiderivative of that. Pretty simple little function. I think that's the one. If I wrote that down wrong, but there's something simple like that that we can't do the antiderivative. If we want to find the integral, we're stuck with stuff like Simpson's rule and trapezoid rule. So don't get carried away just because you can knock down a few little polynomial antiderivatives that you're like, oh, we'll just do the antiderivative. Well, yeah? Just spend the evening with that thing and see what the real problem is there. So the problem with finding integrals is a lot deeper than it looks on day 2 of integrals. Yeah? Okay. So don't write off Simpson's rule yet, even though it's a sort of a nightmarish. But my gift to you, you won't have to memorize them. I'll put them there on the board for you. Any questions there?